We have Ruqing Xu, who is a rising fourth-year PhD in economics at Cornell and the summer's engineering at Microsoft Research. Excellent.
Hi, very happy to be here. Okay, so the starting point of this talk is, suppose we have a principal who wants to take some action to match the underlying state. To do this, the principal designs an algorithm to make predictions about the best action to take. The principal can use the prediction to take an action directly, or the principal can pass the prediction to a decision maker or an agent who then takes an action. The trade-off of doing so is that the agent may have private information that are useful to make a better decision, but the agent may also have misaligned objectives compared to the principal. For example, if the algorithm is a credit scoring algorithm and the agent is a bank manager, bank managers may be more risk averse than a profit maximizing algorithm, either for purely behavioral reasons or due to personal career concerns if they make a bad loan. In this case, the principal faces two design problems are outlined in red in this diagram. First, how should the principal design the prediction algorithm, given that the prediction may be used directly or be given to an agent who could be misaligned? And second, when should the principal pass the prediction and decision authority to the agent, meaning when to make the delegation decision for the purpose of using the agent's private information? Okay, so what do we find? The answer to the two questions are, first, delegating to the agent is strictly valuable if and only if the principal would take the same action as the agent if she were to observe the agent's information. And second, providing the most accurate algorithm, subject to some maximal accuracy cap, which we'll formalize later, can be suboptimal even if the principal can directly use the algorithm's prediction. The most accurate algorithm is not only suboptimal, it can even be worse than providing no algorithm to a decision maker at all. And for the interest of time, I'm skipping off the literature, and we can go directly to the model. It's a very simple model with two players, a principal, she, and an agent, he. There are binary states of the world coded as 0 and 1. The agents share a common prior, mu, which is the probability of state being 1. And here we model an algorithm as an abstract signal whose realizations convey information about the underlying state. And this is the public signal S1 because both agents, like both players, see the prediction of the algorithm. Moreover, we model the agent's private information as a private signal S2, whose realization is only visible to the agent. The structure of the signals are as follows. So in the case of binary signals and binary states, what's important here is these two parameters, P0 and P1, which is the state matching probability of the signals. For example, if the true underlying state is 0, S1 will turn out to be 0 with probability P0. And if the true state is 1, S1 will turn out to be 1 with probability P1. And similarly for S2 with Q0 and Q1. S2, we assume, is exogenously given and are conditionally independent with S1, but this is immaterial to all our results. Okay, so when the agents and the principal, when the players receive signals, they will update their beliefs about the underlying state. And we call their posterior, after observing the first public signal, the interim posterior, and we denote it as mu S1. Which is just the conditional probability of state being 1 given the realizations of S1. And similarly, the final posterior after observing both the public and the private signal, we call it mu S1, S2, the same conditional probability, conditional on the two signal realizations. Now we need one more piece to make this model interesting. Because remember what we have in the diagram, the principal has two choices, right? The principal can either take an action directly with the public signal already, or she can delegate. So because the principal has the outside option of taking an action directly, if the public signal can be perfectly informative, then the principal will never have any reason to delegate. But in real life, this is not what happened, right? Algorithms are never perfectly informative. It doesn't capture everything about reality. And sometimes we do want to delegate to some agents precisely because they have useful information. And we model this in this model by imposing a Blackwell cap on the set of public signals that the principal can choose. And in the case of binary signals, which is our model, this is equivalent to choosing from signals that generate posteriors within an interval lambda around the prior. So the principals are free to choose any signal that generates posteriors within this red interval, but not outside. And finally, the payoff of the agents. They share a common set of actions, which is also binary, and both players prefer to match the state. But they may switch from low action to high action at different points as their beliefs about state 1 increases. And we denote the cutoff belief of the agents as mu p bar and mu a bar for the principal and agent. More details are in the graph. So here, what you see is the players' payoff envelopes, which is the payoff when players are doing their optimal action. And I'm omitting a lot of details here, but what you need to know is the x-axis is the player's belief about state being 1. So what's important is that the payoff of taking action 0 is decreasing in this probability of state 1. And the payoff of taking action 1 is increasing in the same probability. Therefore, both players will switch from taking action 0 to taking action 1 at some point, right, at some cutoff belief. And for example, if this is a principal, then the cutoff belief, we call it mu p bar. And similarly, agent will have another cutoff belief, which we call mu a bar. And in the case where these two cutoff beliefs are not the same, we say the players have a preference misalignment. And this is the case in the right-hand side graph here. So mu a bar is higher than mu p bar. And the interval between these two cutoff points, we call it disagreement interval, because this is the only interval where the players disagree on the optimum action. And how do they derive these payoff envelopes? So if the principal, suppose the principal choose the lower arm, which is to take a direct action, then the principal will just take action 0 before the cutoff point and action 1 after the cutoff point. And we'll get a payoff that's equal to this V-shaped envelope, right, which is basically the maximum of the payoff functions. However, if the principal chooses to delegate to the agent, now the decision power resides in the agent. So the principal's payoff will actually follow the agent's cutoff point, which is mu a bar. This means the principal receives payoff from action 0 all the way up to mu a bar, and only switch to action 1 afterwards. And our result 1 is about when should the principal make the delegation decision. And it turns out that delegation strictly benefits the principal, if and only if the agent's final posteriors lie on the opposing side of the disagreement interval we said before. Okay, so here are the intuitions. On the left-hand side, suppose, so the x-axis of this black diamond point is mu s1, which, if you remember, is the internal posterior of the players after receiving the first signal. So suppose the principal has this posterior, and now the principal is deciding whether to delegate. If the principal does not delegate, then the principal will just take action 1, because this mu s1 is after the principal's cutoff point. So I will take action 1 and get the payoff at the black diamond point. However, if the principal chooses to delegate, then the agent has the choice, has the chance to observe another signal, right, S2, the private signal, which has 2 possible realizations, which will give the agent 2 potential posterior, which is these 2 red dots here. Therefore, the principal's expected payoff from delegation is a mixture of these 2 posterior payoffs. And this turns out to be the red diamond point here. So as you can see, the red diamond is higher than the black diamond, which means the principal strictly benefits from delegation in this case. And to note that this case is exactly where the agent's posteriors, which is these two red dots, are on the opposing side of the disagreement interval. And this is not the case on the right-hand side. For example, one of the posterior actually falls into the disagreement interval, which brings down the payoff of delegation to be below the payoff of not delegating. Therefore, in this case, the delegation is strictly worse, actually, for the principal. Okay, so what we have now is we have characterized whether a principal should delegate for each interim posterior, which is the x-axis. And we also know what's the payoff from delegation, which is the red diamond point. And we want to plot the red diamond point for each x-axis from 0 to 1. And just showing a few examples here. So at the start, the red diamond point actually overlaps with the principal's non-delegation envelope. And then later, it jumps up because now delegation becomes strictly valuable. And now it keeps dropping up. But then here this is where delegation is actually strictly worse for the principal. And finally, it goes back to the curve again. And collecting all the red dots, we arrive at a piecewise function like this. And this would be the principal's payoff if the principal always delegates. However, the principal can be a little bit more smart, right? For example, especially in this area, I shouldn't delegate because I'm getting worse payoff from delegation. So if the principal take the maximum delegation action, I will get a payoff function like this. So this would be the principal's payoff if the principal delegates optimally. And it turns out that this point of discontinuity, row at row, actually turns out to be important in the information design, meaning what public signal should I design? And it's a very simple condition, which is the principal should use the most informative public signal, which is characterized by this lambda, this like maximum Blackwell constraint. If and only if a convexity condition on the posteriors of the lambda and the point row h row holds. Otherwise, the output signal maximizes information about one state while restricting information about the other. What does it mean? So as we can see, this is lambda, which if you remember is the maximum interval I could make my public signals posterior lies in. And look at the posterior at lambda. So this would be the posterior at lambda, this would be the posterior on the other side of the lambda. And the only conditions you need to check is whether these two points, these two posteriors, can be convexified with this row h row, meaning they can be connected with a convex function. And it's equivalent to say that the mixture, like the linear combination of these two posteriors, lies above the row h row point. If that's the case, you should go ahead and use the most informative signal lambda. However, on the right-hand side, this is not the case. So the mixture of these two posteriors lies actually below the point row h row. So in this case, the optimum signal is not lambda, but the blue signal, which maximizes information on the right-hand side, but restricts information on the left-hand side to make the posterior exactly equals row. And some interpretations we can have for the signal in the CS language, it would be this signal would minimize false positive rate. Because when I receive a positive signal, I am very confident about state one. However, it will not minimize false negative rate as it could from the RC curve. One more insights we can get from this graph is that the mixture of these two posteriors is not even suboptimal, it's even lower than the payoff at the prior, which is this black diamond point. This means, in this case, given the agent the most informative signal can be worse than giving the agent no signal at all, right? Which keeps the posterior at the prime. Therefore, this brings us to the final result. Well-intentioned policies aiming to inject more information to the system, such as keeping a human in a loop, using human's intuition, or maximizing prediction accuracy of the algorithm, can strictly worsen decision quality compared to systems with no human or no algorithmic assistance. And I'll conclude by connecting my paper to some empirical evidence. So in recent years, we've seen a lot of excellent empirical work that show the introduction of highly predictive decision aid algorithms often leads to counterintuitive results. For example, underperforming human-machine collaborations. And this paper attempts to provide at least one theoretical explanation. That is, the underperformance of such systems is not only understandable, but even expected if no measures are taken to mitigate preference misalignment between the algorithm and the expert.